Okay, so our first speaker today, this afternoon, will be Casey Decchio from, did I pronounce it right? DCO, okay. From Verisign Labs, talking about abusive IPv6 SMTP.
All right, thanks. So the work that I'm going to be talking about today is a little bit about measurement related to IPv6 and specifically in the abusive realm of IPv6. And I'll try and motivate this a little bit. Okay, so if we give a little bit of background in the IPv4 world and think about some of the problems we face in terms of abusive traffic, one of them is spam, and there, of course, there are various classes of spam ranging from in the spectrum of annoying, you know, your typical pharmaceutical type spam to downright dangerous with malware or something like that, phishing type attacks. Okay, and the sources, of course, are diverse. You might have bots, compromised machines that are actually out there sending the spam directly, or you might have you know, something behind an ISP, and the ISP's SMTP relay is actually forwarding it on, so you have different sources where it might actually appear to be coming from. And so we have this notion of blacklisting in the IPv4 world, and a lot of MTAs subscribe to blacklists. This is fairly commonplace, and because of the reputation system, a lot of things are able to be stopped right at the front door rather than incurring additional processing and the additional risk associated with having to allow things in. Okay, so if we think about the IPv6 analog to this, so at the moment we currently have relatively little data. There may be some data out there, of course, but it is less than we have in the IPv4 world, certainly. Also, at least the current methodology of, you know, a per IP address type blocking is infeasible in the IPv6 world. And there may be other methodologies, but at least in using that specific type of blacklisting just doesn't work in IPv6. So there are some questions in terms of deployment. There may be folks out there that are concerned with deploying IPv6, for example, at their MTAs because of risk of not having this type of protection or filtering at your MTAs. So the question is there a user risk associated with deploying IPv6 capable MTAs without reputation? And then I've kind of mentioned these before. There's potentially added computation, and then of course the allowance of adding malicious content that would have otherwise been stopped through your typical IPv4 blacklisting techniques. So a related question then is, how might operators be able to quantify that risk before deploying IPv6 at their MTAs? And that is the focus of this research. There is some previous work in this area that I'll mention here. Okay, and this probably isn't comprehensive, but here are two notable experiments that have been done. One of them was with an illegitimate domain set up basically with no valid recipients, but it had some advertising out there in HTML pages and so forth, and to try and elicit some spam. Little spam was found, and then there was some on more production type email systems, but they also found, and this was actually done evaluating content and also found little spam. Okay, but let me go on to the current work. So when deciding what type of way, what type of considerations you might need for eliciting spam and how effective it might be, so there are basically three different types that of email domains that you might use that I've identified. First of all is active, one that actually has valid email recipients on the other side. Okay, the other one is illegitimate. Okay, so there have never been legitimate recipients, email recipients on the other side, and then previously active. You've registered a domain or something that used to be active. Okay, several considerations along this way. In terms of effectiveness, there's the volume of traffic, how much traffic you're going to elicit from would-be spammers. There's the targeted versus random. So, there's actually some value into trying to send spam to a someplace where there are actual users. And then there's also the idea that, okay, well, you may be able to look at content versus just who the sender is, and I'll come into that a little bit later. And then there's issues of security and privacy. If you're actually working on an active domain, for example, how do you consider things like security and privacy, and as well as stability of your current system if you're deploying it on an active domain. And then reliability. You don't want to take down your production systems by doing some type of experiment. Okay, so what we propose is something called relevant zero-risk abusive IPv6 measurement. Okay, and so using an active email domain, and I say your domain here, meaning this is something you can try at home. And so the idea is that we get this kind of high-value traffic, high value to spammers, but not only to spammers, or we would hope it would be high value to spammers because there's real users here, but also high value to the operators and users because you're getting data that's associated with your actual domain rather than some fictitious honeypot domain that's out there that doesn't have any legitimate accounts. Okay, so basically the idea behind this is the following in setting this up. So you have kind of two notions of pre-configuration, and the idea is that your production MTAs would be IPv4 only at this point, and only have A records. Okay, and this is we expect that this would be the type of environment that you would be in anyway if you're if you haven't deployed IPv6 yet, and this is where you would be. Okay, so IPv4 only, have only A records, and then you're using some type of reputation system to reject IPv4 spam attempts. Okay, then the changes you would make would be that you would, if you're not already, log these rejections at your production MTAs as they're coming in. And then there would be this sensor MTA deployed with both IPv4 and IPv6 connectivity, as well as corresponding A and quad A records for this host. Okay, and then at the sensor MTA, you would also be rejecting any incoming connections, port 25 connections, over your at your sensor MTA. And then finally, once all that is set up, then you would add a higher order MX pointing to the sensor MTA. Now you may have some questions as to why it's done like this. Let me show you a quick kind of architectural slide to show how this would work, and then I'll explain some of the reasoning behind this. So in the red, if this is this might be somewhat small print, but in the red that basically represents IPv4 transport. In the blue represents IPv4 or IPv6 transport, dual stack connectivity. And so a typical what we would hope, at least for a blacklisted client out there, was that they would initially attempt to connect to the primary MX, then to the and be rejected over SMTP. Same thing for the secondary MX, and then so on until they get to your sensor MTA, at which point they would be rejected with the TCP reset on both IPv4 and IPv6. Now, a couple, so let's see, a couple of the reasoning, a few of the items of reasoning behind this. So first of all, in this way, there's you're not allowing any additional spam from, or initial delivery attempts from known IPv4 spammers, stuff that wouldn't have, would already have been rejected is not going to be allowed in. Okay, so that's the first reasoning behind this. And that's over IPv4 or IPv6. Okay, the rejection log at the production MTA now allows spammers to be identified when they are making their connection attempts to the sensor MTA. Because you've logged those, you can now kind of filter out your true positives attempts from those spammers. Okay, and also because we're sending resets on this sensor MTA, there's going to be no legitimate mail accidentally delivered to the sensor, so you don't get in the case of, oh, I lost my mail. Why was that? Oh, because we lost primary connectivity at the primary MTAs, and so we don't want to have that kind of situation. I don't think anyone would like that. And then, of course, because you have dual stack connectivity, you can have the senders have the opportunity to send to both IPv4 and IPv6 and detect that connectivity at the sensor MTA. And then, of course, for legitimate senders who are not blacklisted, they are going to try the primary MTA first. They won't even know that something is different about your architecture. And in the worst case, where there is some type of problem connectivity issue, then they'll just get rejected at the other one, so you don't have this delivery attempt. Okay, so that's some of the concepts behind this and why it was done this way in kind of what we would call a zero-risk approach. Okay, so the next step is, now we've got this architecture set up, so how do I identify spammers? Well, the IPv4 spammers are known because we have the DNS block list and the rejection log at the primary MTA. So the challenge then, of course, is identifying the IPv6 spammers. So we have to do some type of association between otherwise apparent disparate connection attempts at the sensor MTA. So somehow we have to be able to associate these. And we basically take two steps to, in preliminary analysis, to look at how these might be associated in kind of a, at least initially, a kind of a naive fashion. But there are two steps, and the first one is to actually identify associated SYNs from the same connect attempt, connect referring to the socket API, and then associate different connect attempts from the same host, meaning the IPv4 and the corresponding IPv6. Okay, so a couple caveats that you may have already caught, and we'll bring to your attention if you haven't. But first of all, there is no message content here, okay, and that was deliberate. But the spammers are identified only by association. So spammers are identified, but not necessarily spam, and that is by design at this point. Okay, we also note that spammers are not necessarily going to follow specification, and that's okay. We also believe that, you know, if they can get some value from trying whatever MXs over whatever protocols, then they will. And we do have some data to show some of this, but we do recognize that they're not necessarily going to follow spec, and to be honest, not all implementations do either. Okay, spammers don't necessarily try IPv4 and IPv6 also, nor do they necessarily try the ordering. And the final thing here is that ground truth is nearly impossible to obtain without having observation right at the sending client. Okay, so that's what makes this somewhat tricky. We're only looking at the server side of things. Okay, so first of all, looking at SYN association. Okay, so we have basically using kind of this sliding window to look at the time between SYNs that have the same source port and source IP address. Okay, and we used 25-second. That was actually just based on initial observations, and that might have been because even though we're sending back a TCP reset, sometimes clients were maybe not getting that and doing a kind of a back off. That was kind of our guess as to what we were seeing there, because usually you see kind of a rapid failure and then you see a rapid retry. But let's see, and then so this is the way that we were then looking at, once we had the connect attempts in terms of grouping the SYNs together identified, then we used several ways to identify different associated connect attempts. And so the first one, which I call apparently embedded IPv4 host. Okay, some of these are, if you have like a 6-to-4 address, for example, that's the most common of these that we would see, where you have 2002 and then you have your address and then, or the gateway address, and then you know, a bunch of zeros, and then your host address at the end in the last 32 bits. Okay, so that was the most recognizable. We actually found that a number of other places were doing that as well. So we used that methodology to associate IPv4 and IPv6. Also looking at the DNS pointer record to see if they match, using the 6-to-4 gateway as opposed to the host. We used POF to do TCP fingerprinting of the SYNs that were being sent in, okay, to infer OS, and that helped gain additional insights into what types of hosts we were seeing. And then we were also using ASN, okay, which of course ASNs don't have to be the same between IPv4 and IPv6. but we recognize in a lot of ways that they are, for whatever reasons, administrative or logistic, and so we were using that. Okay, let me summarize this slide because there's a lot of information on here, but basically this is address preference according to RFC 6724. For our purposes means that IPv6 is selected first for get adder info, and IPv4 is fallback except in the case of 6 to 4, in which case the IPv4 is selected first, and IPv6 is backup in terms of preference ordering. And we saw, at least in the most current version of these OSs, the get adder info call actually followed these. Not that spammers are necessarily using that. They might be using their own API, as well as other MTAs might be using their own API for things. But for what it's worth, that's what we found. And so that was also the basis for our ordering when we looked, when we were trying to group these connect attempts, was to look at the order was the v6 before the v4, except in the case of 6 to 4. Okay, and we actually did this on a production email domain with around 10,000 users. We captured traffic between January and November of 2013, and then we, as I just mentioned, did things v6 first, except in the case of 6 to 4. And then we use OS identification with POF. So the next slide shows a graph of some of the traffic that we saw. And so this is daily connect attempts. Now, one other caveat here is because these are connection attempts, we are unable to determine whether or not this is a somebody that an MTA, for example, a ISP MTA that's out there retrying to deliver the same message over and over, or if these are new messages from bots or whatever. But this does give us some idea of activity that's out there. Okay, now I have these grouped into 3 categories. In the blue, the middle line there is IPv6 attempts that we were able to associate with IPv4 addresses. Okay, and then we have in the lowest one there is IPv6 unassociated, and that's because we were not able to associate with anything for better or for worse, you know, spammer or not, and so we had to put it in its own category. And then we have IPv4 attempts at the top. But basically what you see here is we had somewhere on the order of, you know, 10 or 100,000 connect attempts, excuse me, on the order of thousands connect attempts per day, and then we had 2 orders of magnitude higher of v4 attempts. So about 100 times more v4 attempts than v6 attempts at the sensor MTA. Okay, and so anyway, what we see from that last slide, though, by the way, is simply that the traffic is not negligible. There certainly is something there. It's dwarfed, of course, by the v4. We wanted to take a breakdown and look at some of the hosts we were seeing, the OSs and the addresses. Part of the idea behind this was to look at, okay, well, do these look like, you know, legitimate MTAs that just happen to have a bad rap for whatever reason, because they allowed some spam out, or if these are like compromised machines on an end user machine or something like that. Okay, but here's a breakdown in terms of IPv4 hosts that we saw. So we saw on the left-hand side here, you know, 72% of them were Linux machines, but we saw about 11% Windows machines that were, in terms of those that were unassociated, or excuse me, associated hosts, and then some percentage of other that were hitting there. Okay. Interestingly, so when we looked at breakdown of address types, and again, the idea here was to look at if we could identify which hosts of these seemed to be dynamically addressed in some way or other. And so what we were trying to see, now most of these 6 to 4 addresses that you see, about 7.5%, you know, close to 10% if you include the unassociated addresses that were showing up at the sensor MTA, were 6 to 4. And just about all of those were 6 to 4 self-addressed, as opposed to being behind some other host as a gateway. And so, you know, we don't have ground truth here, but we would like to think that this might be something a little bit suspect, as this might be a, you know, brand new Windows machine that was doing its bringing up its 6 to 4 interface because it had no native v6, and but that's the kind of thing we're looking for, is to try and identify these types of hosts. And then you can see we found some percentage of EUI64 addressing, but we also found along the way that those are not always, some people actually deliberately do that even for a, quote, legitimate MTA. They're using EUI64 addressing. So, okay, so a couple items we also found along the way. So Windows XP and 7 actually send 3 SYNs in response to a reject. Okay, well, I'll show you where this comes in handy in just a second here, as opposed to the other OSs which just send a single SYN. Okay, and what that shows us is, so about 75% when we looked at the incoming connect attempts here, in the red you see Windows, which has kind of the large jump there, which shows that about 75% of the attempts from Windows consisted of 3 SYNs, which is what we expected. But there's this other 25% down at the bottom that actually don't have that type of behavior. And if we go to the next slide here, what we did was we took the, we had this kind of hypothesis that with some port-based NATs, that we would actually be seeing behavior where the 3 SYNs that were sent out by a Windows machine actually came from seemingly random source ports because of the NAT. And that doesn't seem to be the case with all NATs, but we did see some of that. And so we wanted to group these without regard to source port to see what things looked like. And if we did that, we actually showed a lot more of the Windows machines that turned up. About half of the ones that we tested, I think, turned out to be have this type of behavior of the 20% that only had seemingly one source port, if that makes sense. So, in other words, this brings us back to, this is interesting, but we were able to identify potentially, and what might be machines that are behind NAT that are hitting these, which might be more indicative of machines that have been compromised or user-type machines as opposed to this other category of MTAs. Okay, one other item we found along the way was that with Windows machines, when they do ephemeral source port allocation, they're actually allocating source ports from the same pool for IPv6 or IPv4, whereas Linux is allocating, and Mac OS X actually, they actually allocate from different pools. And that was helpful in helping us kind of validate some of the findings we were looking at when we did our associations. So if I show this graph right here, okay, this is a graph, and I apologize here, this might be a little bit hard to follow, but in the very middle line that goes up, so this is a distribution here, and the middle line that goes up in the very middle represents a jump for Windows machines in difference between the associated, the source port of the associated v4 and the source port of the associated v6. And 97% of those had a difference between 1 and 500, which closely correlates to the behavior that we would expect from a Windows machine. So it actually a very high correlation with this, which shows that our association, at least for the Windows host, was quite good. We also have this in the middle there. The blue line also follows this little jump in the middle. Okay, and we were trying to look at those. It turns out that about 15%, so that was about 15% of the other attempts. All but one of those are unidentified by POF, and so we believe that actually with the address association that we were doing, we were able to kind of go above and beyond what the typical SYN might lead you to find, and identify those as Windows hosts as well. Those were inferred Windows hosts because of the high correlation. We have a fairly good confidence that those were. Okay, just a couple minor notes that we found along the way as kind of anecdotes. So at one point in our experimentation, we had MTAs from 2 Microsoft ASNs that gave us roughly 1 million connect attempts over a period of about 1 month. So that corresponds to about 1 connect every 5 seconds from each of these /64 networks. And there were few corresponding v4 attempts during that time, and so we weren't exactly sure. We actually were trying to investigate this a little bit, but it was certainly anomalous and something that I thought was interesting to bring up to this group, but apparently not associated with real attempts. So whether it was buggy behavior or what, it lasted for about a month and then it kind of went away. But interesting. And we had something similar with send-mail, actually. We had a large number of incoming requests not associated with v4 that we could see, This was actually an instance of SendMail that we were unable to reproduce in our lab environment as we were trying. But in contacting the vendor or the owner of the MTA, we were able to find out that this is what it was. But what they did was distribute these connect attempts, delivery attempts from the same address and source port in succession over several weeks. So we weren't sure if this was simply reusing the same port because it was associated with the message, or if this was associated with the same connect attempt and it somehow got hung up. But very interesting behavior. We were unsure what had caused it. Okay, but to kind of wrap up here, so reputation of IPv6 internet is still largely unknown. We've presented a kind of experimental architecture here. The idea behind it that you could actually run this on your own network and get some type of feedback as to what things look like if you were to turn it on, and what type of activity you might see not having the v6 reputation that you have currently with v4. And there is some moderate presence of spammers, though the spam content itself can't be confirmed. And we're doing further work to look at what the actual sources are and what things look like in terms of actual distribution. In other words, trying to get closer to ground truth than what we currently have now. I should mention that we are interested in I think it would be very interesting to build a network of this. And if any of you have interest in this and kind of doing a research collaboration and contributing to this, then I'd be glad to hear about it. That's all I have, except for questions.
We have time for a couple of questions. Jeff Houston, the grand v6 experimenter himself.
Jeff Houston, APNIC. I was kind of wondering if you could identify within your process to what extent the MTA software is simply following the MX and using the underlying capabilities of the platform to do 4 and 6. So it's not a deliberate attempt to actually hide behind 6, but it's just, I'm just doing the MX thing, protocols are protocols, versus this idea that most DNS block lists are just v4 lists, and the spammers' interests are well served by deliberately pushing themselves into the 6 protocol. Did you see any evidence of that degree of sophistication in thinking, or are the spammers still just using rocks and hammers?
Yeah, that's a great question, Jeff. And in fact, so there were a couple avenues along this line that we were looking at, and some of our results so far are less than conclusive. I mean, it's really hard to find out what's conclusive at this point, but as you can imagine. But a few of the things that we've also looked at along those lines are, okay, look further into these unassociated v6 addresses. I mean, is it because we're just not associating them correctly, or is this somebody trying to circumvent, just as you had said? And in fact, you know, actually you and I had kind of this conversation about this. You know, what does it look like from inside a provider network standpoint? You know, are the v6 and including protocol 41 blocks just as, you know, just as well blocked as the v4 equivalent for outgoing SMTP, for example? And the other part that we've started to look at is looking at things like address agility, because there's so, you know, there's this kind of long, you know, sparse address range and vast, and so can somebody go in and say, okay, well, I'm going to try this one and it doesn't work, well, let me try this one, and you know, and keep trying. We saw actually very little example of that so far, you know, changing your address within your same/64 or something like that. The other one we have yet to investigate a little bit further, but high interest in doing so.
Okay, thank you.
Okay, no other questions. Thanks very much,
Thank
Casey.
you.